By simply taking an implicit neural representation and replacing its activation function with a wavelet, we can greatly improve its accuracy, robustness, and performance. Implicit neural representations are neural networks that represent a signal, such as an image or a 3D volume, by generally taking in coordinates and outputting the signal values at those coordinates. Research has shown that the activation function plays a big role in the representation's quality, with, for example, sinusoidal or Gaussian functions being popular choices. We instead propose wire, implicit neural representations, with a wavelet as the activation function. We discover how using the wavelet function leads to a whole suite of benefits, including higher accuracy, faster training, robustness to noise, and greater detail preservation in many applications such as CT reconstruction, view synthesis, and others, establishing wire as the state-of-the-art implicit neural representation for many tasks. Let's dive into the details. Implicit neural representations are multi-layer perceptrons that take as input coordinates and output signal values. For example, when representing an image, the neural network takes in XY coordinates and outputs the image intensity value at that location. For 3D volumes, it could take in XYZ coordinates and be trained to output a 0 or 1 value pertaining to whether that spatial location is solid or empty. These multi-layer perceptrons are essentially layers of an affine function followed by a nonlinear function. It's been shown that some standard nonlinear functions used for neural networks, such as the ReLU function, are not the best option for neural representations. Over the past few years of research, the sinusoidal nonlinearity, whose INR is popularly known as siren, and Gaussian window emerged as popular nonlinear functions for neural representations. However, we find in this work that using a wavelet function as the nonlinearity outperforms both the sinusoid and the Gaussian function in a wide variety of tasks. In particular, we use the complex Gabor wavelet function, which is the product of the complex exponential, which has sinusoids as its real and imaginary components, and the Gaussian window. Why a wavelet? It's generally accepted after decades of research in image processing and harmonic analysis that wavelets are in many aspects better building blocks of images than Fourier functions or sinusoids. The reason is that sinusoids oscillate infinitely and are thus not localized in space. Thus, they cannot efficiently represent the types of localized features, such as localized edges, that are typically found in images. The Gabor wavelet, on the other hand, has both a notion of frequency from the oscillating sinusoid and space as the Gaussian window localizes it. In fact, the Gabor wavelet is the optimal function for simultaneous spatial and frequency compactness. It is then insightful to see how the different activation functions work on image edges. Let us consider training an INR on this toy example of representing an image of a white circle with a black background, which is an image that consists of sharp edges that are compact in space. For the sinusoidal nonlinearity, which has compact frequency support, the representation error is spatially spread out, giving ringing artifacts. For the Gaussian nonlinearity, which has compact spatial support, the representation is blurred, giving large error. However, when using the complex Gabor wavelet, which is compact in both space and frequency, the sharp transitions are represented accurately, making wire especially suitable for visual signals. Let's take a look again at the wavelet function. The Gabor wavelet is parameterized by the frequency omega of the sinusoid and the width of the Gaussian, parameterized by S. In fact, you may notice that the Gabor wavelet is a generalization of both the Gaussian and the sinusoidal functions. Set the frequency of the sinusoid to 0, for example, and you just get the Gaussian function. And set the width of the Gaussian function to infinite by setting S to 0, and you just get a complex sinusoidal function. Here, we experiment with different frequency and width parameters for the wavelet nonlinearity of an INR on an image representation task. Again, setting the frequency to 0 gives the Gaussian nonlinearity, and setting the width to infinite gives the sinusoidal nonlinearity. We measure the PSNR of the output, where red here represents the highest PSNR. Observe that the best parameters are around the region marked by the white cross. Observe that an INR with a wavelet activation with these parameters around here perform much better than an INR with parameters corresponding to either just the Gaussian or just the sinusoidal nonlinearity. Thus, the wavelet's generalization of both the sinusoid and Gaussian functions enables us to instead use the optimal choice of frequency and width parameters for superior representation. A strong benefit of wire is its robustness to noise. Suppose we train an implicit neural representation to fit a noisy image. What we want though is a representation of the clean underlying image. Some implicit neural representations, such as, let's say, using Rayleigh positional encoding, end up fitting both the signal and noise equally, resulting in a noisy representation. Others, such as siren with a low frequency, can indeed learn a low noise representation, but they are now unable to represent the sharp features. Wire, on the other hand, can represent sharp features while also denoising the image, implying that it has a good implicit prior for natural signals. Wire also has higher capacity and also trains faster. We demonstrate this on image representation at the top and 3D volume representation at the bottom. Observe how wire achieves higher PSNR and IOU, or intersection over union values, than INRs with other nonlinearities. And it also achieves those high values at a much faster time, as shown in the plots, compared to the other methods. Since wire represents images well, it is also suitable for regularizing inverse problems. As an example, we consider super-resolving an image by 4 times. Wire learns details not visible in the downsampled image and is considerably more accurate compared to other implicit representations for inverse problems. This strong regularizing capability is particularly helpful for challenging inverse problems, such as computed tomographic or CT reconstruction. In CT reconstruction, we observe a small number of projections of a ground truth image and want to then recover the original image. By representing the image as an output of wire, we can reconstruct a high-quality image from the projections. And as a result, wire is better at inverse problems both qualitatively and quantitatively. Wire is also a suitable choice for learning neural radiance fields, especially when trained on only a few images. In this task, we are only given the images for a few views of the scene, and we want a neural network that can reconstruct the scene at novel views. Wire results in visually accurate novel view synthesis. Take a look, for example, at the symbols of the drum set, while other approaches result in ringing or cloudy artifacts. In conclusion, we propose wire that uses the complex Gabor wavelet as its nonlinearity. This results in faster and more accurate representation, robustness to noise, regularization for inverse problems, and an excellent representation for learning high-quality neural radiance fields. Thank you.